Hi, and welcome to the first lecture of the course Computer Vision from Scratch. Today, we'll be formally looking at what is computer vision, how it has evolved historically, what are the methods that people tried before implementing machine learning and deep learning techniques for computer vision applications. So let us get into the lecture. Just before that, let me show you a graph. This is a graph from one of our playlists showing the number of views as a function of the lecture number. So you can see that the first few lectures, first 3, 4 lectures, there is huge number of viewers, but 90% or more than 90%, in fact, has dropped off in the subsequent lectures. So this clearly shows that starting something is easy, but finishing it is not. So I really hope that if you are watching this video and if you are starting this lecture series, you belong to this second category of people who are able to finish. I really, really wish that you can do that along with me. So before we start the lecture, let us take a pledge to finish what we have started. Let us finish the computer vision end to end. I think it will be personally very rewarding for you. It will also be very happy thing for me if you are able to learn it and build a very strong foundation. So let us get started. If you are wondering for this lecture series, what reference material I'll be using, this is the book that I'll primarily be referring to, Practical Machine Learning for Computer Vision, published by O'Reilly. This is a very popular book. You can find it on Amazon. I have purchased like a Kindle ebook format. So it's not that expensive. I think it's in Indian rupees 2000 or something like that for the ebook. So it's a very, very well written book. It also has an associated GitHub repository published on Google Cloud Platform repo. So the repo link is also provided in this notebook. It has almost like 500 plus stars, which is a very, very big deal. So just keep this handy. If you are purchasing the book, I would say it's a very good investment. So there are roughly 500 pages, and there are some chapters in the book which I have found to be something that I should modify a little bit for the purpose of this course. So I have made my own modifications to the table of content of the book, but the primary reference for you will be this book throughout this course. So let us start with a question that many of you may have. This is a very common doubt. What exactly is the difference between computer vision and machine vision? When I started working on machine vision 10 years ago, I had pretty much the exact same doubt. So the main difference is that in machine vision, we are looking at practical usage of vision-based system in industries like manufacturing. So I had worked on a project where I implemented a small camera very close to a grinding wheel. So grinding wheel can be used for slicing a metal, or it can also be used for making the surface polished. And this grinding wheel has a lot of abrasives installed. So if I look at the grinding wheel, not the cross section, if I look at it like just perpendicular to its surface, there will be a lot of sharp abrasives embedded in this wheel, and the sharpness of this decreases with time. So when it is very sharp, if you shine a light on the surface, it will show a lot of white bright spots. Whereas when the sharpness has reduced, the brightness of these spots also will reduce. So you can easily correlate this machine vision setup, in which the camera takes pictures periodically, where you track the reduction in the optical illumination with the degree of wear and tear that is happening to this grinding wheel. So that was a pure machine vision project because you are looking at the system as a whole. You may be using cameras, you may be working on lighting, you may be using sensors or softwares for processing. So all of this together make up the system of machine vision. So in another project which I had worked on, I showed you that already in the first lecture. So this was the paper which I had worked on. Let me show you my Google Scholar. So there was a paper on classifying rice grain varieties using computer vision. And that was accepted to International Conference on Machine Vision. So in this paper also, what we essentially did was we had like a system, a camera-based system, which tracked the track the distribution of rice grains through images, and then we could fit ellipses, least square ellipses around the rice grains, and then using the size of those ellipses, the longer part of the ellipse and the shorter part of the ellipse, we could predict what rice grain it was. This was also a classic machine vision application. So in machine vision, you will also involve hardware along with software systems. There will be camera, there will be lighting, etc. All of these are important. In computer vision, the primary goal is how can you make your machines understand or interpret images or videos. Videos can be split into frames, so essentially they can also be treated as images. And what this means is computer vision is more about you already have the input, you already have the data from your vision system, but you are developing algorithms or theoretical models or machine learning models or normal rule-based systems for maybe applications like facial recognition, self-driving car, analyzing some kind of scanning images from your body, etc. So in computer vision, you have image input already, and you use a machine learning based system, or you use a rule based system, or you use a deep learning system to finally process and derive some conclusion from this image. In this example image that I'm showing, it's like a neural network making a binary classification whether this is a tree or a broccoli. So that is the fundamental difference between computer vision and machine vision. And this course is not about machine vision. This course is about computer vision. So we will be primarily be looking at techniques that will allow us to process and derive information from images. So this is the fundamental difference between computer vision and human vision. In computer vision, you have input as an image. So if it's an image of an apple, you have a computer vision model which takes the image as the input. This model makes a prediction. The model itself can be machine learning model or a non-ML model. I will show you some examples of non-machine learning models, but that makes the prediction. And obviously, as you know, in human vision, you see an apple, your eyes are seeing that apple. The neurotransmitters will produce appropriate signals, and you will eventually receive that information in the brain, which will make you say, hey, this is an apple. So this is the main difference. The processing of whether this is an apple or an orange or something else happens in the model in computer vision systems. For you, it happens inside your brain. So before 2010, it was a time when mostly the computer vision approach was implemented using heuristics. Heuristics meaning manually defined rules. But these days, you will most often find deep learning, convolutional neural network based approaches for computer vision. There are also vision transformers coming. There are generative diffusion models coming. All these advanced techniques are coming, but all these things started a bit later. Before 2010, it was primarily computer vision techniques without machine learning in it. So if you look at this overlap, it's not like computer vision always means that machine learning will be used. That is not at all the case. There are so many techniques in computer vision which has got nothing to do with machine learning. There are also so many techniques within computer vision that are more into deep learning rather than into traditional machine learning. If you are wondering what's the difference between machine learning and deep learning, I'll be briefly talking about that soon in the same lecture. But basically, just understand that computer vision does not automatically mean that you are looking at convolutional neural network. But that was also a problem, right? So before 2010, to process an image and to derive information or to get features from it, you had to manually define some algorithm. You had to manually define certain rules. And most of these rules were implemented using something called as filters. So here, look at an example of this filter. The image on the left-hand side, as you can see, is very grainy. There are a lot of noises in this image, noisy pixels in the image. And you can apply something called as Laplacian smoothing filter to kind of smooth out the image. What are filters? I will show you that in a moment. But the definition of what the filter looks like is very manual. You can come up, if you are a very smart person, you can come up with filters that can do this much efficiently. You can come up with filters that can detect edges in your image. You can come up with filters that can detect circularities in the image. There are all sorts of filters. And the better the filters, the better the capability for you to process the image. This is how it was till maybe early 2010s. This is an example of Laplace edge detector. I will show you what this edge detection algorithm exactly is with a very simple example. But for now, just understand that on the same image over here, two types of filters are applied. In one case, the filter looks like a kernel, 3x3 kernel of values like this. So how is this kernel applied and what is the result? Result is what you see over here. When you apply the kernel over this image, you can get something like this. Whereas when you apply this second kernel in which you are applying the kernel on the original input image, you are getting something like this. And see what is happening here. The kernel is somehow detecting the edges, right? So how is that happening? How does this kernel help you detect edges? We will see that. This is a set of four images that I'm showing. I ran the code in Google Colab to create these edge detections. So the original image was actually not grayscale. It was actually a color image. I downloaded that from pexels.com. So this image, which is the grayscale version of the color image, is what the original image is. Now there are different edge detection techniques called canny edge detection, Sobel edge detection, etc. And Laplacian edge detection. This may look like black to you, like actually there are some edges. If you look closely, I'm not sure if you are able to see this on your screen. Maybe you have to increase your brightness, but you see this person's hair and some edges are actually shown over here. But there are different edge detection techniques based on how the filters are implemented. So let us quickly take a look at how exactly does filters work. So take an example here. On the left hand side, you see an image with the left half of the image is purely white color. Right half of the image is purely black color. Now, let us assume that white pixels are labeled by 1 meaning pixel value is 1, and black pixels, their value is 0. So if you convert this input image into corresponding pixel number format, into corresponding numerical format, this is how it will look like. The entire pixels on the left hand side will be 1, 1, 1, 1, 1, like that. And the entire pixels on the right hand side will be zeros. Now, what we want is the following. If I use this as the input image, I want a type of output image which looks like this. And what is happening here? Here, the output image is only representing the edges in the input image. So the edge should be bright. And where is the edge? Edge is wherever there is a sudden transition in the brightness or color of these pixels, right? So whenever you look at the pixels, this pixel, this pixel, this pixel, they all have the same color. But suddenly when you reach here, when you go from this pixel to this pixel, there is a sudden jump in color. When you go from here to here, there is a jump in color. Here to here, there is a jump in color. White is getting converted to black, which means if you can draw like a line like this line will form the edge, and the output that we are desiring is something like this. The edge should be white in color. That is also what the Scanny edge detector, Laplacian edge detector, Sobel edge detection, etc. does, right? So the edges are generally denoted using white after the filter is applied. Now, what kind of filter can help us get something like this expected output image from this input image? Let's see. So first of all, the expected output image, if you represent it using pixels, it could be like most of the pixels on the left hand side are zeros. Most of the pixels on the right hand side are also zeros because left is black, right is black. In the center, there is a strip which is white. So maybe there are only a row of, column of 2 pixels, and it spans the entire height of the image. Or if there were even like odd number of rows, I could have just denoted the middle odd number of columns. I could have simply denoted the middle column by a series of ones. Here, the example that I have taken happened to have even number of columns instead of odd number of columns. Anyways, so let's assume that what we want is then ultimately, if the above pixel values, if this is the input, assume that this is the input, I want to apply some sort of filter to this input such that I get this as the output. This is my goal. Okay. So now let us see how filters enable us to do that. And let us take this as the filter. Now, why specifically this filter? This filter is the filter that is shown here. You look at this kernel is 0, 0, 0, 0. Then these values are -1, central value is 4. This is exactly that filter. Now let us see the operation of this filter on the input image over here. Okay. So the way filter works is, if I have the center pixel, so this filter is, let's say I put this on top of the input image, and maybe I can try to reduce the transparency. Even if it's not possible, that's okay. So if a filter is over here, you are calculating the value in an output corresponding to this pixel, corresponding to central pixel. Meaning, if you have some kind of input, say, so here the input is these set of pixels, set of 3 by 3 pixels. The filter is this filter. This is 3 by 3. And if the filter is over here, you are calculating the output for 1 pixel. And which is that 1 pixel? The pixel in the center of this filter. Okay. So then how do you convert if this is 1, 2, 3, 4, 5, 6, 7? This is an 8 by 8 image, right? So input is an 8 by 8 image. This filter is a 3 by 3 filter. How do we get 8 by 8 output? We get it by moving the filter all over this image. So we first start from somewhere like this. So the center of this filter will be the first pixel. Now you might be wondering, okay, isn't the filter exceeding the dimensions of the image? Isn't it extending a little bit to the outside the edges? Yes, it is extending. So you can do something called as padding, where you pad the image by a set of zeros, something like this. So this image dimension can be increased by 1 in height and in width, and you pad by zeros, then you make the calculation. Now, how do you make the calculation? So if I am padding it by zeros, the input 3 by 3 pixel, which is the sub set of pixels of this image, will be this, right? And what are those? 0, 0, 0. Okay, not this, this 0, 1, 1, 0, 1, 1, 0, 0, 0. Now what you do is you do element wise multiplication and addition. So you will do 0 multiplied by 0 plus -1 multiplied by 1 plus 0 multiplied by 1 plus -1 multiplied by 0. So basically corresponding elements you multiply and then you add those products all together. So what will happen is the central piece here is 4 and the central piece here is 1. So 4 multiplied by 1 will be there. Now wherever you have zeros, you can ignore those. So all of these you can ignore because you are multiplying all of these numbers by all of the zeros over here. Then what is remaining? You have you multiplied 4 with 1. Then you have a multiplication of -1 with 1 here, and you have a multiplication of another -1 with 1. So the sum of the product will be 4 multiplied by 1 plus -1 multiplied by 1 plus -1 multiplied by 1. So that will be 4 minus 2. So this is how the filter works. In this case, we are specifically interested in the center part. So not in the edge part here, more in the center part. So let us move the filter. The filter is here. Let me make a copy. So now let us consider if the filter was over here, what would be the output? The output would be 0 because all the values of the sub 3 by 3 pixels here are ones. And if you are multiplying that, it will simply become a sum of all these numbers. So 0 plus -1 plus 0 plus -1 plus 4 plus -1 plus 0 plus -1 plus 0. That will be 4 minus 4 equal to 0. So the output, whenever you are moving the filter anywhere here, the output will be zeros. So that is this. The output will be looking like this. Now let us come to the edge, right? Edge meaning wherever the sudden transition is happening. What if the filter is here? What would be the value of the edge? If the filter is here, then you have minus 1. So the value below this is 1, right? So minus 1 multiplied by 1 plus minus 1 multiplied by 1 plus minus 1 multiplied by 1 plus 4 multiplied by 1 plus minus 1 multiplied by 0. This will be the output. So what will that be? That will be 4 minus 3, which is equal to 1. And that is the reason why the entire row here, this entire row is sets of ones. Because when you, irrespective of where you place the filter, whether it's here or here or here or here, you move the filter all the way, you get ones. Forget the edges here. Forget the case when the filter is like this. But other than that, in all other cases, you will get a series of ones. But if the filter was here or anywhere where you have the same set of numbers, you will get 0. And when do you have same set of numbers? When there is no change. And when do you have no change in an image? When there are no edges. Edges mean there is some change, right? That's how you as a human, you know there is an edge. Similarly, if you place the filter anywhere here among the set of zeros over here, the output will again be 0 because filter is getting multiplied by just zeros. So there is no sum. Whereas if you are somewhere like this, right, then you have the output as minus 1 because it will be minus 1 multiplied by 1. Then here also it will be minus 1 multiplied by 1. The rest of the numbers are simply getting multiplied by zeros. Here the filter itself is 0. Here also the filter itself is 0. So throughout here, the output, which will be corresponding to the centerpiece, will be minus 1. Now you might be wondering, okay, if it is minus 1, then why have I written 1 here? Should I not write minus 1? Sometimes you can define rules where if you end up with a negative number, you can take the absolute value. Sometimes you can also normalize. You can say that, okay, my range is from 0 to 255. So I normalize whatever values I get to that range. So it is up to what you want to accomplish, right? But this is a small illustration of how filters work. And here, what did this filter accomplish? This filter accomplished creating an image that looks like this. And what is this image? This image is edge detection. This filter helped us to detect this white color edge, which is the boundary between these white pixels and black pixels. And now if I, instead of this, if I had another complex image, which was like an emoji or something, it can detect that also if you are moving the pixels, if you are moving the filter all over the image. So this is exactly what happens in this canny edge detector or sawbell edge detector, where you move all over, and wherever there is a sudden change in color, that means there is a edge, and that edge will be detected. So see that here there is no change in color. This guy's jacket, it's all the same color, black color. So there is not much edge, and that is the reason why here it's basically black. Here, on the other hand, it's fully white. There is not much change going on. So there are no edges. This area is like fully black. But here there is a sudden transition because there is a white to black transition. Here there is a white to black transition. Here also you can see like a transition in color from a black color to kind of like a brighter color. Same thing here. So all of those edges will be detected by the edge detection filter. Now, this filter can be made more complex. It can be made better, but you might have noticed that it depends on its case-to-case basis. It's very difficult to come up with one filter that fits all requirements, right? It's heavily dependent on your application. So this was not so easy to do. So the early days of computer vision looked like you build rule-based expert systems where you try to define logic. So here the filter was based on logic. Why did we come up with a filter that was like -1, 4, -1, -1, -1, 0, 0, 0, 0? The logic is that if all the values in the pixels below this filter are the same, then -1, -1, -1, -1 will be summed to 4, and then the middle value is also 4. So basically the output will be 0. Output will be black. And that is what you want, because if all the colors, all the pixel values are same in a group of pixels, that means there is no edge there. So that was the logic behind building something like this. Similarly, the second kernel which we used in the above example, this kernel, just look at this. Here also same thing is happening. If there are no edges, what that means is these sum of these numbers is -8 plus 8, which is 0. So whenever there is not an edge, the output will be 0 from the filter. So that was the logic that we were trying to define. But the problem is these classical expert-based or rule-based systems, they have to consider millions of edge cases. And edge cases meaning cases where you could expect something different from what rule you are saying, right? What if there are edges which are different from what this filter can capture? What if there are edges which are horizontally aligned? What if there are vertically aligned edges? What if there are edges like grids? Will this filter work in all those cases? What if you want to identify only vertical stripes in an image like that on a zebra? What if you don't want to identify edges which are oriented horizontally? Then in all these cases, you have to come up with separate rules. So this is where the difference between traditional rule-based systems and machine learning approaches for computer vision differs. In machine learning, we let the machine learning model figure out the logic using data. And specifically, when I say machine learning here, I mean deep learning. Deep learning meaning deep convolutional neural networks. So there is definitely an overlap. So there are computer vision techniques that are not ML. These are non-ML based techniques. There are machine learning techniques which has got nothing to do with computer vision. These are non-computer vision techniques. But there are some techniques where machine learning and computer vision overlaps. And this is where everything is happening in the modern ML-based computer vision systems. So this course is primarily about this intersection where ML overlaps with CV. So is ML-based CV good? Why is it good? Why are we trying to learn ML-based computer vision in this course and not traditional rule-based systems? You already saw one example, but imagine you are building a conventional rule-based system for identifying an image of a cat. And as human, you know that cats, they have ears, whiskers, they have some type of eyes that are very different from maybe another animal like dog or pigeon. There are different characteristics. Now, a pattern that identifies a cat in a traditional rule-based system is entirely different from a pattern that identifies a dog. So if you really want to build a rule-based system that works for all kinds of cat images in the world, or at least for most of the images that you come across, then there might be billions of conditions that you have to take care of. What if in your image there is a dog and a cat? What if the cat is, instead of sitting on the ground, what if the cat is jumping onto a fence? Still, you may want to recognize that in this image, what is being shown is a cat. What if cat is not inside a house? What if it's inside? It's surrounded by a snow environment. So there are so many cases. What if the cat is black color or white color, or it's a mix of different colors? Can you build a rule-based system by taking care of all the different conditions ever? It is impossible, because that then your life will be dedicated to that. This is a scene from the famous TV show Silicon Valley, where Jin Yang, this guy, he makes a classifier. So what he was asked to make was something that can recognize food from an image, and he clicks a picture. But then it identifies hot dog versus no hot dog. Then this guy, Erlich Bachmann, he asks Jin Yang to make a classifier that works for all kinds of food items. But then Jin Yang says, no, that involves labeling, like first of all, scraping internet data and labeling a lot of images as pasta, burger, spaghetti, whatever. And that's like a manual, boring scut work. So although here what Jin Yang is building is a deep learning system effectively, the scut work idea that is being discussed here is what is relevant for rule-based systems. In rule-based system, you'll be manually doing that work of identifying all the different conditions in which an image can appear or a cat can appear in an image, and then taking care of that, all the edge cases. It's boring. It's not the most efficient way to teach an algorithm anything. Just think about ChatGPT. If you are asking ChatGPT some question, it's not that somebody who has built ChatGPT is kind of pre-coding the questions that it is expecting, and then pre-coding what response it should give. That's not how ChatGPT works. Nobody explicitly coded the large language model LLM to give certain type of reply. Instead, the only thing which LLM was asked to do was learn how to predict the next word given a set of data, given a paragraph, learn how to predict the next word, then add that to the paragraph, and that will be your new paragraph, and now learn to predict the next word. Like this, the next word prediction capability of large language models resulted at some point in emergent properties like translation, being able to do coding, being able to, although not very in a very good way, being able to do math, etc. So this was very different from the way you would build a rule-based system. So machine learning models, the great thing about not using rule-based system, but instead using machine learning model is that you are not going to explicitly tell what to look for in an image. You are not going to say, hey, look for whiskers, or look for brown eyes, or look for tail. None of that will be described to the machine learning model or the deep learning model when you are building a cat versus dog identifier. And this is what makes modern deep learning techniques so powerful and so efficient that most of the modern applications like self-driving cars, or even healthcare, if there's a robot that can perform a surgery, this is what deep learning is, what most of these applications leverage. You might remember there was a conversation between Elon Musk and Jan LeCun about whether Tesla uses convolutional neural network or something else like vision transformers. But anyways, irrespective of that, all of that are deep learning techniques. So this is the power of machine learning models over conventional rule-based systems. Just look at this example of optical character recognition. So OCR, optical character recognition, is if you are inputting a scanned image of a textbook, say you have a physical textbook, you scan the textbook to have a image of a page like this, and then let's say you want to digitize this textbook. In traditional world, how would you do this? You have to figure out how to detect individual sentences here. So if this is the textbook, you would first want to eliminate, if there is a lot of noise, let's say there are a lot of noisy grains or something like this, then first of all you have to figure out a way to filter out this noise. So you want to figure out how to remove all these things, and that itself is a huge challenge. Then after that, you will have to figure out how to extract groups of words or sentences from this image. So you might be making a filter move all over this image from top to bottom, left to right. And then once this image detects, and what if the filter is partially detecting something like this, it should not then be able to provide any output. But then this filter, it should have conditions defined, such as whenever it detects words with spaces in between them, treat them as separate words wherever the space is occurring. But then maybe there is another case where you don't want to treat those words as separate. So there are these multitude of rules. And then once a word is identified, figure out how to split the word into individual letters. And then to figure out what this individual letter is, whether this is H or P or M, maybe you would have decided a rule that whenever a vertical thing and a kind of a rounded thing is seen, it can be H, it can be P, it can be Q, it can be B. There are many possibilities, and it can also be H. Then you will say, okay, so just a vertical thing and a circular feature is not enough. Maybe some other features are also should also be considered for identifying an H from a B or P or Q, etc. Then you will define that rule also. And as you can already imagine, this is very cumbersome, very inefficient. And that's the reason why most of the former techniques prior to deep learning were very, very bad. Mostly computer vision was meant for very, very niche applications. And most of the other advanced applications was just meant to be done in a research setting, in a very controlled research setting. So these systems, rule-based or heuristic word means something like rule-based. It doesn't work properly because you are handcrafting rules. Like, how do you recognize P? Maybe a straight line descending on the right side and then a circular thing on the other side. And then you say, once these features are extracted, you may pass it into some sort of if else conditions, or maybe you may use machine learning techniques like decision tree. So decision tree is not a deep learning technique, it's a machine learning technique where this tree will help you classify whether this is a P or Q or something else. And then the issues are this, right? If there are many fonts, so what works for this font? What if my handwriting, what if I write H like this? What if I write like this? What if I write like this? There are many different ways in which I can write H. Humans can read all of these. And what if I write like this? What is this? This is also like an H. Even a baby might be able to say that this is an H. But can a traditional heuristic rule-based system can recognize this? Probably not. So variability in fonts and styles, these were an issue. If the image quality, if you upload a very bad, so this scanned image looks okay, right? But in reality, this can look very bad. Like what if you have like if the book is very thick and when you scan, the text on the edges, this part will look a bit curvy, right? Because of the curvy shape of the book itself. Then what would you do? The sentences may not be exactly parallel to each other. How would you take care of that? What if the background of the text is not exactly white? What if there is some stain? What if the book is very old and it has like a dark spots or something like that? So the orientation was an issue. Printed versus handwritten, as I shown, this was an issue. Now, in English language, you should look at certain type of features in the image. But what if you are suddenly looking at some other language? What would you do? Sometimes characters could be overlapping. So let's say this is one way to write character. Somebody else may write it as like this. And you might have noticed, like in the modern handwritten recognition, like if you're writing on your mobile phone, there is a handwriting option, right? It's very good. It can detect many type of handwritten characters, and that is because it is not rule based. It is machine learning, or rather deep learning based. If the contrast between the background and the text is good, that is also a problem. If you have paragraphs, so for example, here you have one paragraph, here you have another paragraph. Now in another textbook, this will be a completely different style. All of these things, it's impossible for a rule-based system to take care of. So that is why when earlier I said there are millions of edge cases to take care of, it is true. These 10 I have mentioned, but then each of these 10 can be expanded into another 100 issues. And then 10 is just a small number. There are even more number of issues. So the number of issues that you have to manually take care of will be never, ever ending. So that is why deep learning gained popularity, and this can be probably entirely attributed to a neural network architecture called as AlexNet. This changed the history of computer vision in 2012. Till around 2012, it was very difficult to even implement neural networks for tasks like proper image classification. Although there were models, there were very good image classification models. Nothing was as good. But AlexNet, introduced in 2012 by Alex, that's the first name of the first author, Ilya Sutskever. So you might notice Ilya's name. He was one of the former co-founders of OpenAI. I don't think he works at OpenAI anymore. He quit and he has started another company, which is almost like $1 billion company now. And Professor Geoffrey Hinton, who recently won Nobel Prize in Physics for founding, for being like a father of machine learning. He's not, I don't think anyone calls him as a father of machine learning, but basically for laying the foundation. So these three people were part of this paper, which proposed AlexNet. You can see that the name AlexNet comes from the first name of the first author. And this entirely changed the history of computer vision. And computer vision wouldn't be where it is today if not for AlexNet. So I'll tell you what AlexNet accomplished. I'll also show briefly its architecture, although in this lecture, I don't expect you to understand the whole thing. But this starting of this course will never be perfect if I don't mention about AlexNet. So this paper, by the way, currently has more than 170,000 citations. So this screenshot I took from Professor Geoffrey Hinton's Google Scholar, and you can see the AlexNet that was proposed. So when they proposed it, obviously they will not name it as AlexNet because it was probably a name that came later. But this was a deep convolutional neural network used for ImageNet classification. And ImageNet is this data set, which is a very popular data set for training your neural network. So many researchers used ImageNet data as a benchmark. So if you can perform very well in the ImageNet data, you have a very good ML model. So that is what they did. And this is the rough architecture of AlexNet. They had convolution. They had something called as max pooling. They also used rectified linear unit activation function instead of tan hyperbolic activation function. I will show all of that. But this is the rough architecture of the AlexNet convolutional neural network. So what exactly did they accomplish? So there was this ImageNet challenge running at that time. Even this was also there in 2015. That is when the ResNet was introduced, which was another novel architecture. They actually literally obliterated all other models, but AlexNet started everything. So AlexNet won the ImageNet competition challenge in 2012 by a huge margin. So their error rate was 15.3%, whereas the second best model has 26.2%. Usually the difference between first and second would be very minuscule, but this was the first time deep learning models could actually learn patterns in the image with such high accuracy. And until this point, deep learning, meaning models with have many deep layers, neural networks with many deep layers, up until this point when AlexNet was introduced, was purely a research topic. Whereas by the time AlexNet came, it showed without any doubt that deep learning could have outperformed every single traditional machine learning model like support vector machines or random forest, etc. We are not going into the details of how support vector machines or random forest work, but we'll be going into the details of how deep learning models work. AlexNet also showed that you could increase the training speed by a huge margin by using GPU instead of CPU. And I would say even the growth of NVIDIA started somewhere around this point, because initially NVIDIA, they were building graphics card for gaming. And now gaming is also still an industry where graphics card is extensively used. But now if you look at why NVIDIA is such a big company, it's because graphics card, I mean, the GPU, graphical processing unit, is primarily used for building or, training AI models. So AlexNet was one of the first papers which showed that deep learning models can be trained very fast by using GPU instead of CPU. And they also combined a few different things in one single model. It's not that rectified linear unit was used. It was introduced for the first time here, but rather it was used for the first time successfully in this model instead of sigmoid or tan hyperbolic activation function. If you don't know what these mean, don't worry. The detail is not what is important. What is important is just knowing what AlexNet accomplished. They also introduced dropout regularization to reduce overfitting, because if you do overfitting, you will fail in the ImageNet competition, because you won't be making good predictions on the testing image. They also introduced max pooling so that you could enhance the extracted feature values. And then they also did data augmentation. Like if you have an image of a cat like this, you could do a lot of things to get more training data from this one image. So you could crop the image, you could randomly rotate it, you could randomly crop it, you could take a mirror image like this. All of these are valid images of cat, which is extra data you can get out of the existing data. So these are data augmentation techniques which this paper introduced very successfully. And basically what happened is almost pretty much overnight, deep learning took over all the traditional ML approaches, especially for computer vision. And since then, very few people have in fact, worked on even machine learning models. Today, if somebody talks about computer vision, you by default think about deep learning. You don't think about traditional machine learning approaches. And then later, this also expanded to natural language processing, robotics, healthcare, etc. Amazon Robotics, they use robots which have a vision plus sensor system. In healthcare, robots could perform surgery with the help of vision system. In NLP, you are using literally deep learning models nowadays, like the transformer architecture is a deep learning model. So all these things happened ever since the initial deep learning success happened due to AlexNet. And this triggered the revolution that we see today. So there is another very common doubt which you may have as you are watching. What exactly is the difference between machine learning versus deep learning? The main difference is that in machine learning, models like decision tree or random forest or support vector machine or linear regression or multi-regression or logistic regression, in all these ML models, you need to feed the model features. And what are features? Features could be anything that describes your input. So if you have an input image, somehow you have to extract the features first, and then you are feeding those features into your model so that the model can learn how these features correlate with the final output that it is supposed to predict. So now if the features are curviness or something else from these input images, you have to extract those features and feed it into these models so that the model can learn on top of those features and then make a prediction. And these are called machine learning based approaches. In deep learning, on the contrary, you don't manually perform feature extraction, which is what makes deep learning very, very powerful. Instead, you have a deep neural network with multiple hidden layers, not like what is shown in this image. This image is purely representative, but you have a neural network with multiple hidden layers, which automatically does feature extraction and also classification. So you don't do feature extraction and classification separately. And this makes deep learning so much more powerful because the place where you struggle the most is in feature extraction. If you want to create something like a chat GPT, how will you manually extract features from the text that is available on all over the internet? It's impossible. Instead, with deep learning approaches, the only thing which you do is you train your deep learning model to predict the next word. If it makes a good next word prediction, you kind of say that the loss is less. You have good, the weights or the parameters of the deep learning model is good. If the next word prediction is very bad, then the loss is very high, which means you modify the weights a little bit. And then this is repeated over huge amount of data. And this is how the deep learning model learns. What features does it detect? We don't know. We have to use sophisticated techniques to figure out what exact features is this model looking at to make the prediction. Sometimes the features that these models are looking at may not have anything that is physically related to what you see in the image. Maybe it's more abstract. But at the end of the day, deep learning models can do this without a human intervention. This is what makes the deep learning techniques very powerful. In general, however, deep learning is, of course, a subset of machine learning. Machine learning means all the techniques where you can basically map an input to an output without explicitly teaching them the rule to make this mapping. In rule-based systems, however, you have to explicitly teach how to map an input to an output. Like a function, if you are defining a function, you are explicitly saying that if this is the input, predict this as the output. But ML techniques broadly do not do that. So that brings us to the last part of this lecture. What's the difference between a normal neural network and a deep neural network? In a normal neural network, which we will implement in the next lecture for a simple image classification problem, there could be one or maybe max two hidden layers, not more. In deep neural networks, you will have multiple hidden layers. So these are hidden layers. This is input layer and this is output layer. Here, this is the input layer. This is the hidden layer and this is the output layer. So this is a shallow neural network. This is not deep neural network, and this is a deep neural network. So this is the last part of today's lecture. So before we wind up, I simply want to congratulate you for finishing a very small step in this whole journey. This series has as I'm predicting, it has more than 30, 35 lectures. So this data is not from this series, obviously, because I'm still recording it, right? But as I mentioned, starting is not easy. Starting is easy, but finishing is not easy. So you must feel very proud about yourself for taking that small step of finishing through this, going through this lecture and finishing it. But please remember, you are here and your goal is to reach somewhere here. So feel good about yourself, but also please pledge yourself that you will finish what you have started. And if you can figure out some ways to make yourself accountable by either putting some comment, or if you do not like putting public comments, just put it from some other account, like where your name is not there. Just put a comment saying finished lecture number 1, and next I'll be starting lecture number 2. Or if you have a friend or group of friends who also wants to learn computer vision, gather them along and try to learn together. And as you are learning together, do this same thing by keeping each other accountable. And also write good notes while you are learning, and feel free to share the notes with people. I think it will help everyone. So with that, let us wrap up today's lecture, and I'll be very much looking forward to meeting all of you in the next lecture. I hope you are enjoying the series, and I am also enjoying it so much teaching it. And in the next lecture, we will start with implementing some simple ML neural network based models. I mean, without any deep learning framework, I will start with a very simple neural network model without any activation function, simple linear model for making a classification, and we'll see what kind of accuracy we get. And from there, we will build and we'll learn more complex topics. So thank you so much for listening. We'll meet again in the next lecture. Take care until then. Bye.